sections left, 9.6 and 9.7, center of mass and rocket propulsion, but it's not the easiest of two sections. Okay, so, and to be honest, your book, especially for 9.6 center of mass, gave me a headache. So I can only imagine how you would feel if you were reading through that piece. So try to pay attention as much as possible during this during the first hour of this lecture at least, because what I'm going to be doing is I am going to be using material that I had prepared earlier for a different book, okay, to present this topic of center of mass to you, to provide you a different and easier perspective than the calculus-based approach that your book uses, okay? So here we go. Bismillah. Okay. I'm showing you two objects. One is a two-dimensional square, and another is a three-dimensional cube. Now, if I ask you, point towards the center, okay, of each one of these, most of you are not going to have a problem doing that. It's obviously right in the middle of the circle, right in the middle of the square, and right in the middle of the cube. So far, so good. Turns out we have been using something so far, whether we have been doing it in chapter 3 and 4 with the equations of motion, or 5 and 6 in forces, or 7 in work, or 8 in power, or 9 in conservation of momentum so far. We have been doing something, but we have not actually been saying it out loud. So let me give you an example. When we were talking about two cars colliding, for example, or when we were talking about a block that is falling down or a ball that's going up, and we drew the free body diagram, what did we draw the object as? Remember? Every single time we draw a free body diagram, we draw it as a simple dot, and then we start doing things like these. Yeah. Now, this dot actually is what we call the center of mass, and what we're going to be spending the next hour talking about. Turns out it has profound consequences, and it is so sort of, for the human brain, not from a physical or mathematical point of view, for the human brain, it is such a simple concept that we have been using it all along without even thinking about it. So I am unable to, great. Where is it? Yes, I'm supposed to be showing a demo, but okay. Demo is demo. Let's show a demo. Okay, I am unable to find the demo file, which isn't the best option to be in. But let's try a different way. Here we go. Let's take a look at this video and try to notice something in it, and then we will explain it. So this guy is going to throw something, and it looks very, very weird. Okay, it's just floating around, bobbing around until it falls down. Now we'll toss the same object, but in dark and with this, what we call the center of mass painted in orange, and take a look what happens. Do you notice anything? Did anyone notice anything? The orange dot was being a perfect projectile. Although when we're looking at the full object, okay, when we're looking at the full object under just normal lighting, it was just going, okay, weird. Nothing predictable about it. As a matter of fact, if I just gave you that and told you to calculate something about it, the first question you're going to ask me is, using what? Okay, it's impossible to predict the behavior of such an object. Yet, when we painted the center of mass, and in the dark, it was a perfect trajectory. Here's a baseball bat, and a baseball bat, if you're into baseball, you would know is very thin on one end and very, very heavy on the other end. And if I throw it up, this is the trajectory it's going to take, which is very, very unpredictable. But even then, when you're looking at it, you can see it's going in a certain trajectory, a shape that looks like this. But you can't really determine, okay, based on what is that happening? Now, if I actually draw the center of mass, which you will notice is actually not in the middle of the stick, and we will be coming back to this in a bit, okay, it is slightly off to the heavier part, and you just attempt to trace that bit, again, it's just a perfect projectile. Let's look at it from a different point of view before going into any mathematics. This is a triangle, and you are trying to, yes, excellent, Ryan. You're trying to balance a ball on top of it. If you've ever done that, you know it is extremely difficult to balance a ball, okay? But when you're trying to balance a ball, you're trying to make the ball as close to the center as possible so that it would stick there and wouldn't fall. If you try to do the exact same thing with a baseball, and if you try to put it at the middle, it's not going to work. You need to put it slightly towards the heavy end to be able to balance it. And the point of balancing, okay, is what we call the center of mass of a person, as the center of mass of an object. Okay, now the center of mass of a normal human being is somewhere around here. Okay, if you are as fat as I am, then your center of mass is probably more towards your stomach. Okay. What about systems of particles? Okay, we figured it out. We have an object. It's in the center of mass. It's somewhere in the middle. It's maybe slightly off to the heavier part. We'll figure out how to do the calculations later. But what about systems of particles? What if I have more than one object? Then what do I do? Say, for example, this is a ball that I have, and the center of mass is right there in the center of the ball. Yeah, we've all played them at some point in our life. Lulu? Here's another one. Again, the center of mass of that ball is in the center. Now, where is the center of mass of this full system? Anyone has any idea? If I want to take these two as one object, as one system, where would I put the center of mass? Component at the middle, في الوسط بينهم, between them. Excellent. It would be right here in the middle. Okay? So if I'm drawing a free body diagram of this thing, I'm just going to take this middle point and draw all my forces here. And it's going to work just perfectly well. Okay. What about now? One is slightly bigger than the other. The mass of one is more than the other. The center of mass of each one alone is in the center of that ball. But where would my center of mass shift now? Excellent. To the right a bit, to the heavier one a bit. Yeah? So now if I want to do the free body diagram, I'm going to do it here. Okay. Now that we know what the idea is, we start to approach the mathematics of it a tiny bit. I've drawn a whole bunch here. Let me explain first. So we have ball 1, ball 2. Ball 1 has mass 1, ball 2 has mass 2. Ball 1's center of mass is at x1. And ball 2's center of mass is at x2. So far, this is all straightforward. Now, I've written XCOM or XCOM, which stands for X center of mass. And we have agreed already that if this is the middle point, it's going to be slightly to the right or slightly to the heavier side. But now what if I want to actually know exactly how much to the right? Okay, now I'm no longer happy with just knowing it's شوية لليمين. I want to know exactly كم لليمين to do some calculations. How do I calculate it? Turns out the way we calculate it is we do a few stuff, we simplify, and we end up with this. We end up multiplying m1 with x1, m2 with x2, and then dividing by the total mass of both objects, m1 plus m2. Okay? I have set my 0 to be here. Once I have set my 0, this is x1, this is x2, and I calculate it from the same point. Can I calculate it from a different point? Can I have my 0 here, for example? Yes, that is absolutely fine. Can I have it here? Can I have it here? Can I have it here? I can have it in any point I want, but of course the calculation is going to be way, way more complicated if I don't use a nice 0 point. Okay? Bear in mind, this XCOM that you're going to get is going to be exactly from the 0 point that you have chosen. Okay? So if you choose your center, if you choose your 0 point to be somewhere around here, one will be positive, one will be negative. Okay. Now this is for 2 particles. If I have many particles, more than 2, what happens? Well, I will have to do the same thing for each and every single particle. So m1 x1 plus m2 x2 plus m3 x3 for however n particles I have. And then I will have to divide it by the total mass of all the particles combined. Okay, or all the objects combined. And I'll denote that by capital M. The easier way to write it is 1 over capital M, which means 1 over the sum of all the masses. Sum, this is the summation notation, from I equals 1 to n objects, mi xi. Okay, or as I remember it, MIXI. Okay. Let's see if we understand this. Consider the Earth and Mars in their orbit around the Sun. Where is the center of mass located for this three-body system? So you have the Sun, you have Earth, you have Mars, and you're going somewhere. These are their orbits. Where is the center of mass? I'll give you a minute to try it out. Remember, we don't have numbers. This is just an idea sort of thing. So D, closer to Earth. And the correct answer is indeed D. It is closer to the Sun than it is to either the Earth or Mars. Why? Because the Sun is actually so big and so heavy that it is very, very much heavier than either Earth or Mars, or even both of them combined. Okay, which means that the center of Mars is going to be somewhere around here. Bonus question: do you know how much would it be for the entire solar system? Turns out, for the entire solar system, it would actually be pretty much at the center of the Sun, plus or minus a tiny bit, because you will have planets on the left side. If this is my Sun, I will have planets here and planets here, and they will cancel each other out. Okay, this is a representation of how big the Sun is compared to either Mars or Earth. Okay. What about 3 dimensions? We did everything in 1 dimension, nice enough. What about 3 dimensions? Well, it's the exact same calculation applies, but in each one of these 3 dimensions. So instead of MIXI, now we have MIXI, MIYI, and MIZI. And instead of doing all 3 together, we can do all 3 separately, each one on their own. What I'm going to do is, I'm going to just use the straight vector r for location from, if you remember from our chapter on displacement. Okay, and my r is going to be simply x in the I direction plus y in the j direction plus z in the k direction, which means I can combine them all into one equation, and I'm going to come back to that in a bit. Okay. Now, this figure shows a uniform square plate from which 4 identical squares at the corners will be removed. Where is the center of mass of the plate originally? Where is it after removing square 1, squares 1 and 2, squares 1 and 3, squares 1, 2, and 3, and if we remove all 4 tiny squares? So no calculation, just general. So I'll leave this on screen again for a minute. And we're going to be doing this quite a bit in this lecture because I think it is important to understand how this works. Oops. Okay, think of it a bit. While I prepare to bring up something. Here we go, sorry. Okay. Let's continue. I'll return to sharing the entire screen. And I'll do them one by one. I will also do something that I mention here, and I'm not sure if it's actually legal for me to do so or not on SQ servers, but I'm going to be doing it anyway. I will be sharing a PDF of this book, okay, Fundamentals of Physics by Halliday Resnick, which explains this chapter in a way better way. As you can see, I have used this book to prepare for this lecture. Okay, and I'm going to share it with you. Hopefully, this would be easier to follow than your existing book. Okay, so let's take a look at each case one by one. Where is the center of mass of the plate originally? Pretty much every single one of you said it correctly. Here in the center. Excellent. Everything is uniform. Now, if I remove square 1, that square is a bit lighter and the other 3 are a bit heavier. So it's going to slightly move to here, closer to 3. Now, if I remove both squares 1 and 2, the top side is light and the bottom one is heavy. But it is equally unheavy and heavy on the left and right side. Okay. I have not rejected anyone from coming in. Let her come in using her. Let her try to join using her SQ account.
دكتور
Yeah.
اليوم في مشكلة في الميتينج، حتى في السيشن الماضية طردني وما أقدر أدخل، يمكن في مشكلة في الجوجل ميت.
One second. This is weird. This should not happen. What is her ID? Do you know what's your friend's ID? Or which Maryam? Is it Maryam Al-Abriya? Or some other one? Just give me her name. It's enough. So Maryam what? I have 4 Maryams here that show up. Okay. Okay, fine. What just happened? Okay. All right. Okay, she should get an email now from me. Okay. She should be getting an email now. If she clicks on it, hopefully she will be able to join. Okay. So if we remove both squares 1 and 2, we are going to move from here down to somewhere around here, below the center point, but still in the center. Now, if I remove 1, 2, and 3, the answer is a bit obvious. It's going to become here. And if I remove all 4, then we're going back to the center, because what I actually end up with is something that looks like this, with equally cut off parts of all 4 corners. Okay, now let's think of something else. If we look at a figure where we have 2 rods, okay, what if there is a gap in the middle? Actually, that is an excellent question. Let us try it out. What if we have a gap? Okay, so if we take a square like this, and we have a gap in the middle. We have equal distribution in all 4 sides, right? So what we end up with is that the center of mass will stay at the center. There's no square at the center, so the center of mass is going to be in thin air. But at no point did we stipulate that for the center of mass to exist on a physical point. It can be in thin air. That is fine. When we remove both 1 and 3, this is what it looks like. Where do you think it's going to be? So it is equally imbalanced from 2 corners, so it's going to remain in the center. Excellent. You're getting the hang of this. Now we have 2 rods. Think of them as 2 pans. Both of them of length L. What are the coordinates of the center of mass of this L shape? Okay. Think of them as exactly uniform rods, no changes whatsoever, no mass distribution, everything is equal. We have option 1, L over 2, L over 2, so here. Option 2 will be somewhere here. Sorry. Option 2 will be somewhere here. L over 2, L over 4 will be here. L over 4, L over 4 will be here. And L over 8, L over 8 will be somewhere here. A, D, 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 A, D, A. Okay. So most people are saying A. Some people are saying D. Let's do the calculation. This one is actually not very obvious. Now, if I look at the center of mass of each rod independently of the entire system, so just the rod itself, okay, we are going to have it right in the middle, right? So M and M right there. So let's tabulate. Each one of them has a mass of M. Each one of them has a length of L1. Okay, the center of mass of them is L1 is going to be at X L over 2 and Y axis 0. The other way around for L1, the other way for L1, it's going to be here at L over 2, 0. For L2, it's going to be here at 0, L over 2. Now, if we take L over 2, L over 2, okay, it's going to be here. But if you remember, as always, the X and Y axes don't speak to each other. So we need to do our equation. Mire, sum over sum of m's. And the x-axis, this will be m L over 2 plus m 0 over 2m. It's L over 4. For the y-axis, it's going to be exactly the same. So actually, contrary to what we would think, this is not our center of mass. Our center of mass is actually going to be here at this point. Is everyone clear how we reached this? Is anyone confused? The Qanun is from here. Or before it. From here. This is the first instance of it appearing. Cool. Mariam, I'm glad to see that you have managed to join back. Okay. I usually never kick anyone out of my lectures. So if anyone does face the problem of being kicked out and not being able to rejoin, I'm pretty sure you all have WhatsApp groups or methods of communicating with each other. Do get in touch with your friends over there and do what Mariam did. Just let me know that you got kicked out, and then I'll invite you again like I did. Okay? All right. Let's do this one more time. I will remove everything from here. And I will take just this to a whiteboard. Okay. Here we go. Okay. Now, just looking at L1, not the entire system, where is its center of mass? It's a uniform rod, nothing funny about it. It's going to be right in the middle, right? And right in the middle is at a location that we call x is L/2 and y is 0. For L2 alone, the dot is going to be here. And this is at x0, y L/2. Now, in the x-axis, we have x center of mass equals 1 over total m sum of mi xi. 1 over 2m, because each one of them has a mass m. m1, or they're both m's, so I'm just going to call it m, not m1. M x1 is L/2 plus m times 0. This will give me ml over 2 times 2m. The m's cancelled, and it will give me L/4. So xcom is L/4. If I do it for y, I will again get the exact same calculation, L/4. So my com is here at point L/4, L/4. Okay. Let's do one that is slightly more complicated, and I'm actually going to use a sample problem that is from that other book rather than our books, because I don't like headaches, and I'm pretty sure you don't like headaches either. Okay. Here's the problem. Figure, Ahmed, I'll upload it on Moodle today, the full PDF, okay, of the whole book. Okay, all right. Figure 9-4a shows a uniform metal plate P of radius 2r. Dina, they're exactly equivalent. They just explain things in different ways. The concepts are the same, just one of the books presents it in a slightly different way than the other. Okay, so it's exactly the same thing. Okay, take a look at either one, whichever one you find easier, use that one to understand. The concepts are exactly the same. Our book has, how do I put it? Has more integral calculus in it. But we have a problem here in that most of you have not done integral calculus yet. So not all of the problem are doable by you in our book. Okay. Ryan, I'll upload them again. I uploaded it. Maybe there was an error. I'll upload it again. Thank you for reminding me. Khalil, I agree. Okay, so figure 9-4a shows a uniform metal plate P of radius 2r, from which a disk of radius r has been stamped out, removed in an assembly line. The disk is shown in figure 9-4b. Using the xy coordinate system shown, locate the center of mass com P of the remaining plate. So this is the plate that happened. We have a big plate and a small circle is cut out of it, but not in the center, to the left. Not as nice as that with these squares. Okay. So let's take a look. I'll remove this. Okay. My original is 2r. My removed plate radius is r. Where is my center of mass? Small circle, big circle, plate. Each one of them, okay, the small circle, its own center of mass is right in the center. The big circle, its own center of mass is again in the center. Okay. Now we know it should be somewhere close to the center to the right. Excellent. The question again is, how much to the right? What is the number? So let's do it this way. I'm going to draw them all in one straight line. Okay. And I'm usually not very good at drawing. Each one of them has a mass. Each one of them has a center of mass. That's fine. Now, here is how they align. The center of mass of the small circle is to the minus r from the big circle, right? So our 0.00 here is in the plate. ليش هذاك السنتر على الجانب مع الجانب راسمنه بالضبط انه من وين طلعته حطيته تحته على طول. Okay. Now, if I look at the center of mass of each one of them, center of mass of PSC, and where is the location of the center of mass? Okay. For XS, it's going to be at minus R here. For C, it's going to be right at the center, so 0. For the plate after removing, we don't know. This is what we want to find out, XP. Masses, plate has a mass MP, the small circle MS, and the full thing, plate and circle, is mass circle plus mass plate. So far, we have not actually done any calculations. We have just been writing down, okay, what we have so far. Rayyan, you're correct. We are not given the mass. So we are simply saying the mass of the full circle is the mass of the plate plus the mass of the circle. This cannot be wrong, right? So if this was 1 kilos and this was 2 kilos, then this would be 3 kilos, 2 plus 1, right? If this was 10 kilos, this was 20 kilos, this would be 30 kilos. Yeah, we're not assuming anything else. That's why we're not using any numbers. We're simply putting letters. Okay, XCOM is equal to M1 X1 plus M2 X2 plus M3 X3 over M1 plus M2 plus M3, etc. Now we put it in. XC here is equal to, if we are assuming that this equals 1 plus 2, okay, then the center of mass of this full thing would be equal to M of the small circle, X of the small circle, plus M of the plate plus X of the plate, divided by the total sum of masses. We substitute everything in that we know, okay, we end up XP equals minus XS over MS over MP. This is what Rayyan said. That's not given. Can it be minus R equals XP? It cannot be, mainly because it is obvious that the right-hand side is heavier, okay? If for any reason, though, this side is heavier than the other, then it can be. It can be here in a blank space. If your question is, can it be in a blank space? Then yes, it can be at a blank space, no problem. But if your question is, in this case specifically, can it be here, then it cannot, because obviously more weight, more mass is on the right-hand side. Okay, so how do I find out? Now, there's a way to do it. Okay, and I'm going to show you how. You don't need to remember this, but I will show you that even when we don't have mass as a number, we can still find a lot of things in physics by looking at relationships. Okay, so mass is equal to density times volume. Volume is thickness times area. This is all high school stuff. So mass equals density times thickness times area. So ms divided by mp is equal to density S over density P, thickness S over thickness P, area S over area P. Here's the question though. Since this was a uniform plate, what is the relationship between density S and density P? They were from the same plate. They are equal. So this is simply 1. They are from the same plate. What is their thickness? Again, equal. So this is simply 1. So my ratio of masses reduces to simply the ratio of areas. Area S is area S. Area of P is the full area minus area S. Again, I'm not using any numbers so far. This is the amazing thing about this problem. Okay, no numbers so far. Area of the small circle is pi r squared. Area of the full circle, pi of 2r squared. Area of small circle again, minus pi r squared. The pi's cancel out. And this reduces to simply a number, 1/3, 1/3. Suddenly, xp equals minus xs ms over mp. Ms over mp is simply 1/3. We have gotten rid of ms and mp. We just got a number now. So xp equals minus xs 1/3. We know xs is minus r. So minus r times minus 1/3. Sorry, minus r times 1/3 is simply r/3. So our center of mass is going to be here. If this is 0 and this is 2r, it's going to be here at r/3. Okay. This is the amazing thing about this problem. We ended up with a number even though we had 0 information and 0 numbers. Okay. Back to 3 dimensions. We said that RCOM is xi, y, j, z, k. We also said that this means we can generalize whatever we have done to simply this. Okay, so this is really nice. Okay, and I remember this as Miri, M-I-R-I, and I remember it because of that biscuit. I don't know if you eat that biscuit. I used to eat it a lot when I was young. It's a red biscuit Miri, صغير مع الجاي. Okay, so this is how I remember it. RCOM is equal to Miri over sum of all the masses. So 1 dimension, XCOM, MIXI, 3 dimensionals, Miri. Well, I'm trying to make it close enough. I don't have Miri here, so it's M-I-R-I. So I'm trying to bring it close enough to my head. Okay. MRCOM is simply this. If I bring M up here, And if we remember something, V is equal to dr by dt. This is from chapter 3, I think, or chapter 2. I don't remember anymore now. Yeah, this is exactly why I did not say Mary. I'm trying to avoid this. Okay. In the British sense, we call them a butler, a helper. Okay, so VI equals dr over dt, which means that since I already have the R center of mass, I can also have V center of mass, which means that I have something that is rotating in a crazy fashion, and I want to use one of my really nice equations, V equals U plus AT, V squared equals U squared plus 2AS, S equals UT plus half AT squared from our earlier chapters, the really nice ones. Yeah, if I want to use one of those, which V should I use here? Which U should I use here? I should use V center of mass. Since the center of mass explains the whole thing, the trajectory of the whole thing, I can simply use V center of mass. It's just the total mass. I brought it down up from down here to up here to multiply it. That's it. Okay. So, and the same way, if I differentiate it again, I can have a center of mass acceleration. And then if I and that means that I can actually have the sum of all forces just by looking at the center of mass. And this is why we can write sum of F is equal to MA. So whenever we have been doing this so far, and we have been drawing it as a dot, mg, and tension, we have been doing this. We have been doing this because we have actually been using a center of mass. Okay? So, to recap, we have RCOM equals 1 over m MIRI. Then we have VCOM equals 1 over m MIVI. Then we have ACOM, which is 1 over m MIAI. Okay? And we can use these quantities in any equation we have learned so far. So we have learned that W equals F dot D. We have actually been using the AC of mass. Okay? When, for example, we have been using power equals FV, we have actually been using the center of mass. So we've been using it all along. We just haven't mentioned its name. Okay? This is why we can take any randomly shaped object, treat it as a dot, and shove it into an equation. Because what we're actually doing is we're looking at the center of mass. What time is it? 1:02. Okay, we still have time, hopefully, to finish this. Yes, that's what I just said, Ryan. Velocity, acceleration, and displacement. This is not clear. Let me do it this. Yeah. Everything we have been doing so far, we have been using the center of mass. We just haven't said it by name. Okay, let's see if we've understood. A system is made of a ball A of mass m moving to the right at speed 2v. So ball A, mass m, moving to the right at speed 2v. And ball B of mass 3m moving to the left at speed v. Before the two balls collide, okay, I have made a mistake because this is supposed to. Okay, I've made a mistake. A, B, 2v, v, m, 3m. Okay. Before the two balls collide, what is the magnitude and direction of the velocity of the center of mass of this system? Let's see if we can do this. I will also do it on a piece of paper. CBD A Okay, let's do it together. Okay, so you have ball A, mass m, ball B, mass 3m. This is going at 2v to the right. This is going at v to the left. Remember, vectors. Bcom is equal to m1v1 plus m2v2 over m1 plus m2. Here we go. One. Okay. So m2v, let me write it in a different way. So vcom equals 1 over m sum of mi vi 1 over m plus 3m m times 2v plus 3m times minus v because of vectors 1 over 4m 2mv minus 3mv equals minus mv over 4m. The m's cancel out. We end up with minus v over 4. So the correct answer was option A. Okay. All right. Let's do a couple of applications. Now I'm looking at your book, okay, and I'm looking at the examples of your book, and it covers exactly every single thing that we have done so far. Okay, they just have more complicated examples. أيوة. I need to finish explaining the concepts first, and then we can do the problems. We also have, we no longer have labs, so we have tutorials every single week from now on, and this is by design, not by accident. Okay, so we can do many more problems, yes, but first we need to finish the concepts. Okay. All right. So now that we know what a center of mass is and how does it work, okay, let's look at the motion of a system center of mass. We've already said that because we can propagate this whole center of mass thing, and that we have already used the concept of center of mass without actually mentioning it, right? F equals MA, and the A we have been using is center of mass. So Fx is MA center of mass X, Fy is MA center of mass Y, Fz is MA center of mass Z. What do we learn? F net is the sum of all external forces. M is the total constant mass of the closed system, and closed is in bold for a reason. ACOM is the center of mass of acceleration. Okay. What else does this tell us? We know another definition for force is dP by dt, right? Correct? Do we have a momentum center of mass or not? Noor, I'll come back to your question in a second. Yes, we do have a momentum center of mass. Why? Because momentum is simply mv, right? Which means that so far, the momentum of center of mass equals m velocity of center of mass. Correct? Okay, good. What else? can we learn from this? In a closed system, what happens to the velocity of a center of mass? If I have an object that moves through space with no net external forces acting on it, okay, it's a closed system, all the forces are internal, nothing external, okay. Now the internal forces, different directions, different magnitudes, blah, 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 okay, but no external forces. What happens to momentum? What have we been saying so far in this chapter? We have been saying that momentum is conserved, right? So now if we say that our final momentum is equal to our initial momentum, which we've been saying so multiple times so far in this chapter, this implies that mv center of mass before equals, and I'm actually going to use capital M because it's all the masses together, mvcom after. Correct? Now, by definition, since this is a closed system, we cannot get more mass or less mass. So mass before has to be equal to mass after. So I can take it away. And we end up with vcom before equals vcom after. So for example, تو خلص العيد الوطني, we saw fireworks. Yeah? We already used the example of fireworks in conservation of momentum when we spoke about explosions, right? Now, since the explosion is not an external force, it's from inside the firework, okay, momentum must be conserved. The total mass of each one of those tiny firework lighty thingies is equal to this total sum of masses when it was a single piece, when it was launched, right? Which tells us that the V of the center of mass before the explosion is equals to the V center of mass after the explosion. Have you ever wondered why in a plane accident, okay, whenever we hear La Samahallah, there's a plane accident, okay, why is it that the first thing that many people, many investigators ask is, where is the debris? يبحثون عن الحطام. Why? Well, it has to do with this. If they put the location, you have seen it in on TV, they get those tiny, yellow thingies, number 1, number 2, number 3. And if they take the locations of every single piece of debris that they can find, put it into a computer, calculate MIRI of each one of these small particles, they can extrapolate back, okay, the center of mass. They can explore back the velocity of the center of mass, okay, and hence the momentum of the center of mass. Okay, now if we can, all right, find what is the velocity of center of mass using our thingies, and we can find the black box, صندوق الأسود, it will tell us what was the velocity of the plane. The velocity that the car tells us or the plane tells us is the velocity of center of mass. Now, if the velocity of the center of mass before the explosion, okay, before the plane crashes, was equal to the velocity of the center of mass that was determined using all of these debris that was collected, the first thing that they know is this was not due to an external attack. There was a problem within the inside of the plane. But what, for example, if they get the VCOM, V center of mass, after the collision using the computer model, which is different than the one in the black box beforehand, before the plane crash. What does that mean? Usually, what that means is that your momentum has not been conserved. Excellent, Ahmed. It means that there's another object in our system that we have not taken into account. Okay, maybe it was a missile, maybe it was a rocket, maybe it was a bird that went into the engine. We don't know, but it's a starting point. We know إنه سبب الحادث كان خارجي, فعل خارجي, and it was not internal. Okay. It's 120. We have a whole bunch of examples, which I will post on Moodle anyway. But I think we can stop at this point. Yeah, we can stop at this point. We are left with 9.7, rocket propulsion, which hopefully we will finish in the next lecture. This chapter has taken the most number of lectures from us so far, if you have noticed. Most chapters before this we finished within 2 lectures. This has been ongoing for 3-4 lectures now. And the main reason for that is because there's a lot happening in this lecture. Also because the next few upcoming lectures and chapters will depend heavily on this one as well. So we need to take our time with this. Okay, now one by one. First, I think Noor was asking me something. التسارع والسرعة لهم كتل.